Okay. And this one is an equation for a wave. Okay. So let's look at if we have an equation for the wave. Okay, what we can handle is like that. So the equation for the wave, because it describes the oscillation of all the points. So it's a function of both the position and the time. Okay, and it's given by 6 sine 2 pi x plus 4 pi t. Okay? The only given condition is this equation, but we can know a lot of stuff about the wave from that equation. Okay? In fact, the equation is a complete description of the motion, so you know everything. So, A, amplitude, AM equals to what? 6 meters. Okay, they are in the standard unit. B, angular frequency. Omega, what's that? 2 pi. Okay, you can keep 2 pi, so 6.28, something like that. What is the unit we should put here? Angular frequency. What's the angular unit for the angular frequency?
Radians per second. Radians per second.
Yes, it's the same as angular speed. So it's radian per second. That's the angular frequency for this wave. So in question?
Isn't 2 pi k? Isn't 4 pi?
Yeah. So like the 4
Oh, sorry. 4 pi. Okay. It's kx minus omega t. The number between the number in front of t is omega. Okay, not in front of x. So it's 4 pi. And C, what's the quantity we are calculating? Wave number. What is wave number?
Is that K?
It's K equals to what?
2 pi.
2 pi. Okay.
Same units, radians per second.
The unit, okay, for the wave number is not radian per second. Okay. In fact, okay, you can see what is the unit of it's 1 over meter. Okay, you can think about K is proportional to the reciprocal of wavelength, right? Wavelength has a unit of meter, so the reciprocal has a unit of 1 over meter. So this is the unit of the wave number. Any question here? So they are the quantities you can directly read from the wave equation: amplitude, angular frequency, and wave number k. Okay, and here we say that for the oscillation, omega has a central role here. From omega, you can calculate a bunch of other quantities. And for the wave, omega is still important, but there is another important quantity, k. So if you want to calculate all other quantities, you need to know both the angular frequency omega and wave number k. Okay? So now, D, to determine the period t, which quantity here can enable us to calculate period t? Omega. Between omega and t, what's the relationship?
2 pi over negative.
So 2 pi over Is it?
It's supposed to be a negative.
Okay. So,
Negative 2pi.
No.
yes. Okay. Because omega equals to 2 pi f and f equals to 1 over t. That means omega equals 2 pi over t. So t equals to 2 pi over omega. So for the relationship between all these quantities, we wouldn't give you all the relationship directly. We only give you a few fundamental ones on your formula sheet, like this one. But you can always derive the relationship between any two quantities. Okay. E, frequency. So again, from omega, right? Frequency equals to omega over 2 pi. So, F, wavelengths. How can we calculate wavelengths?
Whatever the wavelength
From which quantity you can calculate wavelengths?
Frequency is equal to 1 over wavelength. Frequency is equal to 1 over wavelength. Right?
Not frequency. Okay. Which quantity here is related to wavelengths?
Period.
Okay.
K.
Okay.
You have to use T to find it.
These quantities are one group. Frequency, period, angular frequency. These are related with each other. Okay. They're talking about the time aspect of the wave. Wavelengths, wave number, these two belongs to a different group. They are related with each other, and they are both of them talking about the spatial relationship. Okay, the spatial pattern of the wave. These are temporal, the time pattern of the wave. Okay. So to calculate the wavelength, you need to know k. So what's that? What's the relationship between the wavelength and k? Do you remember?
1 over k. 2 pi over k.
2 pi over k, right? Okay? So you can see from those equations. So here you have omega equals to 2 pi over f. Here you have k equals to 2 pi over lambda. So they are the fundamental equation. And here you have one more. P equals to 1 over f. Okay? So, of course, you can calculate all these quantities with this equation. Any question here?
Yeah, isn't there another equation for period that relates with K?
There is another equation for period related with omega, which is if you combine the two, you get omega equals to 2 pi. Oh, sorry. Omega equals to 2 pi f. So 2 pi over. If you use this one for here.
So I seem to remember an equation that incorporates K.
Okay, you are talking about the relationship between k and omega.
Yes.
That's for velocity, yes.
Okay.
There is another relationship between this group and this group, which is in terms of the speed of the wave. V equals to omega over k, or lambda over t. Okay. So for all these equations, please think about it. There are something about this group, temporal pattern. There are something about this group, spatial pattern. But these two equations, actually these two equations, okay, relate this group and this group. Okay. So you can get that's 2 pi over 4 pi, so 0.5 seconds. That's 4 pi over 2 pi, so it's 2 hertz. So the period is half second. The hertz is, the frequency is 2. So 1 second, you finish 2 cycles. And the wavelength is 2 pi over 2 pi. Okay, so it's 1 meter. The wavelength is 1 meter. Okay, so that means spatially it repeats its shape every 1 meter. Okay, so the wave is for every 1 meter you get same shape. Okay. And again, I would like to emphasize the understanding of these things, why you have this group and this group. So this is talking about repeating a long time. This is talking about repeating after the distance. So like here, period t equals to 0.5 seconds just means if you look at any point along the wave, after, so it will repeat to the same position every 0.5 seconds. So if t equals to 0, the position oscillates to here. After 0.5 seconds, it will back to here. After 0.5 seconds, it will back to here. So that's the temporal pattern. And lambda equals to 1 meter means that if you look at the wave, so if this point, the position is this high, the oscillation. So 1 meter away from it, the oscillation will give you the same height. Okay, 1 meter away from it, same height. So, okay. Now, determine the speed and the direction of the propagation of the wave. So, how can we calculate speed? So, omega over k equals to 4 pi over 2 pi. So, it's 2 meters per second. You can also use lambda over t. You see, lambda is 1 meter. Okay. And the t, the period is 0.5 meters. So again, you get 2 meters per second. Okay, that's the speed of the wave. One thing you need to know is that the speed of the wave can be calculated from omega over k or lambda over t. Okay, but this quantity, speed of the wave, is more fundamental than this quantity. So by changing this quantity, you are not going to change speed of the velocity. The reason is that if you have a same system, okay, the speed is 2 meters per second. That's something you usually cannot change unless you change it to another system. So if you change the omega, if you double the omega, the speed will not double. Please note that. What will change? The k will also double to maintain the same speed. Okay. So if you change omega, you are going to change k. If you change the lambda, you're going to change t. Speed is key, the same. Remember when I do the demonstration, whenever I try to make a fast oscillation wave, right, I'll always get a very crowded wave shape. When I try to make a slow motion wave, I always get a less crowded, okay, pattern. So they change accordingly to maintain the same speed. So this is a constant. These two change proportionally to each other. Finally, in which direction the wave is propagating.
Towards the negative x.
Okay, yes. Positive side there means negative direction. Okay. So if we get like 6 sine 2 pi x minus 4 pi t, that one means the wave propagate to the positive direction. Okay, so this is the positive direction. This one means negative direction. Okay.